Hello, everyone, and welcome back. In this video, we're going to introduce one of the most fundamental topics in not only this lecture series, but in all of analysis in mathematics, and that is sequences. We'll start by defining what a sequence of real numbers actually is and introduce how we write it, and then we'll start talking about what it means for a sequence to converge. This is something you might be familiar with. We're going to talk about limits. And from there, we're going to look at convergent sequences and ways that we can show that sequences do not converge. This will naturally lead us into a discussion of Cauchy sequences, and we'll also talk about what it means for a sequence to be bounded. Let's go ahead, let's jump right in, and let me show you what I mean when I discuss sequences. At the very highest level here, a sequence is really just an infinite list of real numbers. So we could think of something like maybe 1, 2, 3, 4, 5, right? And I think you get the idea here. And you just are listing off all of the natural numbers, right? And this is an infinite list. So everything is in there. The 100th element of this sequence is 100. The millionth element is 1,000,000. Or maybe you can just alternate between ones and minus ones ad infinitum, right? So all of the odd elements are -1, all of the even elements are +1. Or maybe you could say 1 1/2 and 1/3 and 1/4 and 1/5 and so on and so forth. And you just keep taking 1 over each natural number. Now, if you put that one into your calculator, you can see that something very interesting is happening that's not happening with the other two sequences. And that is that you're getting closer and closer to 0. This is what we're going to talk about when we discuss convergence. But just for a moment, let's abstractly define or think about how we write a sequence. We can write a sequence of real numbers in the following way. We write x sub n, and each one of these is going to be, for our purposes, a real number. And what this means is the subscript tells you what number of element in the sequence you have. So n is an element of the natural numbers, and x sub n is the real number corresponding to that element in the sequence. So you could have x1, x2, x3, x4, x5, and so on and so forth. In this example right here, the very first one, x sub n is just equal to n. The nth element of the sequence is the nth natural number. In this case right here, example number 2, we have xn is equal to -1 to the power of n. And in the third case, we have xn is equal to 1 over n. And in all of these cases, n goes from 1 to infinity. So that means that one way you can always think of a sequence is as a function, right? So this is something that we learned probably in a calculus class. And you can always think of this as a function with a discrete domain. So maybe we sketch these things the way we do with regular functions, except along the horizontal axis is n, and along the vertical axis is x sub n. And then what we can do is we can say at n equal to 1, we have some point x1. At n equal to 2, we have another point, say x2. And 3, we have x3. And 4, we have x4. And this goes on and on and on and on. For every single natural number that you pick, you can find an element of the sequence here that corresponds to that natural number. This should be 6, and this should be 7. Now, one other alternative way that you can think of these is filling in numbers on the number line. So you can hide the dependence on n, and you could say, here's my number line. And so this is the set of real numbers. Let's put 0 right in the middle. And what we can do is we can just put points on this number line. So we could say here's x1, and then here's x2, and maybe here's x3, and here's x4, and here's x5, and here's x6, and so on and so forth. I'm just kind of randomly putting these on, but I want you to see there's two different ways that you can think about these things, either as functions, functions of the natural numbers, or as just points selected from the real line. Now, what we're really interested in is the behavior as n goes to infinity. And again, if you've taken a calculus class, you're familiar with these concepts because these are called limits. We want to know, so what happens as n goes to infinity? Now, let me give us a definition here for a convergent sequence. So as I said, most of the lectures are going to start with definitions, and then we will see what we can cook up based on those definitions. So we say a sequence xn, now here's going to be our symbol, converges to some L. L stands for limit in the real numbers. So the right arrow means converges as n goes to infinity. So if and only if, well, for all epsilon greater than 0, there exists some capital N in the natural numbers such that, so this will correspond to epsilon, such that if n is chosen larger than capital N, this guarantees, or this implies, that the difference between the elements of your sequence and the limit in absolute value, so remember the absolute value measures a distance on the real line, if this is smaller than epsilon. And we say if there exists a L such that S dot T dot, that's just a short form, xn approaches L, we say xn is convergent. And we also say, so if there doesn't exist one, so otherwise, we say xn is divergent here. So we have some new nomenclature for our vocabulary. And now we have a precise way of saying that something actually converges, that a sequence converges. And this right here, this xn minus L is less than epsilon, is just a percolation result. It says that if you look far enough in the sequence, everything is gathering around the limit point. And the epsilon here can be chosen by you. You say, I want everything within some small number of the limit. Say I'm interested in 10 to the minus 2. Well, what this definition says is that I can always look far enough in the sequence to guarantee that every point beyond that is within 10 to the minus 2 of the limit. Maybe you want more precision, 10 to the minus 5. Still a positive number, still a valid choice for epsilon. So let's see this in practice. Well, we have the following example. So we claim that, so my third example from earlier, remember I said 1 over each natural number, it looks like this thing is going into 0, right? If you type them into your calculator, 1 over 8, well, 1 over 9 is smaller, and 1 over 10 is even smaller, and so on and so forth. It looks like we're getting closer to 0. How do we prove it? Well, that's what this example is meant to illustrate. So this says that if you define a sequence by 1 over each natural number, then this thing is converging to 0. So the proof here, PF stands for proof. The way that we're going to prove this is we're going to say, imagine epsilon has been given to you. I don't care what it is, just pick a positive number. Okay, so let epsilon be bigger than 0. Well, then we need, so if we want to show this thing is convergent, we need to find a capital N such that if I look beyond capital N in the series, then I have 1 over little n minus 0. In my case, L is equal to 0. So let's just make a little note. L is equal to 0 here. This is less than epsilon. Right? That's what convergence says. So just look back at that definition. It says if I look far enough into the sequence, no matter how small of an epsilon I choose, I'm always going to be close as long as I look far, far enough into this thing. Okay. So that is, we need to solve the inequality. 1 over n is less than epsilon, all right? So that's getting rid of the minus 0. That didn't do anything. And getting this thing is always positive, so we don't need the absolute value. Well, then, what we see is this is the same as, so this is equivalent to, so you can multiply both sides by 1 over epsilon. And essentially what you want is, multiply both sides by 1 over epsilon and then both sides by n. This is the same as looking for a capital N that is bigger than 1 over epsilon. But here is where our axioms of the Archimedean ordered field come in. Remember, the Archimedean property, so the Archimedean property guarantees the existence of a natural number n such that capital N is bigger than 1 over epsilon. Remember, that's what the Archimedean property says. It says if you have a positive number, no matter how big it is, no matter how small it is, I can always find a natural number bigger than it. So 1 over epsilon, that's a positive number. It could be 100 trillion or it could be 3. Doesn't matter. I can always find a natural number that's bigger than it. The important piece here is that the value of capital N depends on, or it corresponds to, the value of epsilon, just like I pointed out in the definition here. So then, so if n is greater than or equal to capital N, we get, well, 1 over n is less than or equal to 1 over capital N, right? So we inverted, so we flip the inequalities, which is smaller than epsilon, which again comes from flipping the inequalities. And therefore, so thus, 1 over n minus 0 is less than epsilon for all n greater than or equal to capital N, which proves that we are in fact converging to 0, right? So what does this actually say just in words? It says that if you pick some epsilon, doesn't matter how big, how small, I can always find 1 over the natural numbers that is smaller than that value of epsilon, right? That's what the Archimedean principle is essentially doing in this case. Okay, let's look at another example of a convergence sequence. Let's let R be less than 1 in absolute value. So it's between -1 and 1 exclusively. And in this case, we claim that if you continually raise this thing to a power of a natural number, this converges to 0 as n goes to infinity. Okay, so for example, 1/2, you take consecutive powers of 1/2, these things, it becomes a half, a quarter, an eighth, a 16th, a 32nd, a 64th, 128th, and so on and so forth. It gets small very, very fast, right? This is what's called a geometric sequence. Okay, how do we prove it? Well, we're going to proceed in the exact same way that we started with the last one. Let epsilon be greater than 0. So this is picked, it is fixed. I don't care what it is. I'm going to show no matter what this value of epsilon is, I can still make the proof work. So we need to find a capital N such that n greater than or equal to n implies, well, that r to the power of n minus 0 is less than epsilon. Now, the first thing I want to point out, this is, or maybe I'll just say equals, I'll put it in a different color so I can point it out to you. This thing is just the absolute value of r to the power of n. I'm just rewriting it, right? The minus 0 is not helping at all here. It's just making things look uglier than it needs to be. And so I'm just going to write it like that, right? The absolute value of r all to the power of n. So first of all, case 1, if r is equal to 0, that's a valid choice, right? The absolute value of 0 is less than 1. So this is a possibility. Then we can just take n equal to 1 to prove the claim. Why? Well, if r is equal to 0, then r to the power of n is always 0. And that means that r to the n minus 0, again, 0, which is always smaller than epsilon, because by definition, we assumed epsilon is larger than 0. So we can always wedge that one in. That's a sequence of just zeros over and over and over again. Doesn't really do much for us. So let's suppose r does not equal to 0. Then we need to solve. So if we invert this inequality here, this is equivalent to saying 1 over the absolute value of r all to the power of n is bigger than 1 over epsilon. So you can compare this to the previous example. It's very, very similar to what we were doing. Now, you might be tempted to take nth roots here, but technically, we're building from the bottom up. We are going to assume that we do not have any square roots or any nth roots yet, right? So we're not going to worry about that. We're going to do it without taking roots. Okay, first of all, since the absolute value of r is less than 1, this tells you that 1 over the absolute value of r is bigger than 1. So we can write, so what I'm going to do, since that's bigger than 1, I'm going to write it as 1 plus whatever the part of this that's beyond 1, right? So it's bigger than 1, so I can always write it as 1 plus something else. For some p greater than 0, right? So again, think about, my age is bigger than 1. So I am 31. That means that I am 1 plus another 30 years, right? So that's exactly the same idea here. So thus, we can take 1 over the absolute value of r to the n. Well, this becomes 1 plus p to the n, which this is just rapid multiplication. So this is 1 plus p times 1 plus p all the way down. You do this exactly n times. Now you do all of this multiplication out. Maybe you want to use the binomial theorem to get the proper expansion, but this is going to give you 1 to the power of n plus n times p plus a whole bunch of other stuff plus p to the n. And I'm tucking everything away on the inside because it doesn't matter. 1 is positive and all of this stuff is positive. So that tells me this is bigger than n times p, right? So it's very, very crude, extremely crude how we're doing this, right? I just want you to see that this thing is a bunch of positive numbers. So if we just take out, the only thing that we want to keep is that n times p. And why is it that we want to do n times p here? Well, we're going to use the Archimedian principle again to show that this is bigger than 1 over epsilon. So by the Archimedean property, there exists, so this backwards E means there exists a capital N such that n times p is bigger than 1 over epsilon. Again, if p is not bigger than 1 over epsilon, then I can add p's over and over and over and over again until I am bigger than 1 over epsilon. 1 over epsilon is just a positive number. Again, it could be 3 or it could be 100 trillion, whatever it is, doesn't matter. So then, taking n greater than or equal to capital N, we get, well, what do we have here? 1 over the absolute value of r to the n. And then after all of the manipulations before that, this becomes bigger than n times p, which p is positive, n is greater than or equal to capital N. So I get capital N times p here, which is bigger than 1 over epsilon, which implies that the absolute value of r to the n is less than epsilon. So therefore, r to the n converges to 0 as n goes to infinity. Right? So we argued from the definition, this epsilon definition. So what you can see here is that convergence means that you're sort of bunching or percolating or coalescing around a single point, right? That's what we call the limit. Now, if everything is bunching around the same point, that would mean that also elements of the sequence are starting to bunch together as well. So there's a term for this bunching together of elements of the sequence, and it's referred to as a Cauchy sequence. So it doesn't mean that you're approaching a limit. It just means that your sequence elements are starting to bunch up and come together. Now, this is named after a very, very famous mathematician, especially in the realm of analysis, Augustin Louis Cauchy. He was a French baron born in 1759. And he is one of these people that we're going to see over and over and over again in this lecture series. An extremely important figure in the beginnings of modern mathematical analysis. So in his honor, we call these sequences that start to bunch up element-wise a Cauchy sequence. So we say a sequence xn is called we'll put it in red because it's a definition, a Cauchy sequence. So it's named after the mathematician Cauchy. If and only if for all epsilon greater than 0, so I'm using the upside down A, this means for all, this is just mathematical shorthand. There exists the backwards E, we've just saw that in the previous proof, so I have lots of shorthand because there's lots of writing. This is corresponding to epsilon again. Such that if n and m are greater than or equal to capital N, this implies that xn minus xm is less than epsilon. Now, I want you to really take a second with this and absorb what it's saying, right? This is not saying that you have a convergent sequence now. It is saying that your elements are bunching up. So it says if you look far enough in the sequence, that's what this line, n times m is greater than or equal to capital N, far enough down the sequence, then every single element is going to be within epsilon of every other element. That's what this final piece here is telling you. And again, much like the definition of convergence, epsilon gets to be chosen, right? This works for any epsilon you want. Now, a lot of people have trouble with Cauchy sequences because they seem to sort of say something similar to convergence. And in fact, we have the following theorem, which says if xn is a convergent sequence, of real numbers, then xn is a Cauchy sequence. Now, what's the translation into English out of sort of math speak here? Well, if your sequence is eventually going into a single point, so a limit L, then everything is getting close to the limit. And that means if everything's getting close to the limit, then everything is getting close to together, right? You're sort of percolating around that. And so all of the elements of your sequence far, far down it are falling into the same area. So let's prove this. This is a nice little proof. It's a perfect application of the triangle inequality that we proved in the last lecture. So let's say, suppose xn is convergent. Now, we know from the definition what that means. That is, xn approaches L and R as n goes to infinity. So there's some limit point here. Now, we're going to say let epsilon be greater than 0. And we're going to do a little trick that you may not have seen before, but you're going to see it a lot more in this class. So then, since epsilon over 2 is positive, this is a completely positive term. So you gave me epsilon is equal to 1/10. I said divided by 2. I want 1/20. So since this is positive as well, there exists a capital N corresponding to epsilon such that n greater than or equal to n implies xn minus L is less than epsilon over 2. So I'm using the definition of convergence here. I'm using epsilon over 2 as my positive number. That's how close I want the elements of this sequence to be. And I know, because this thing is convergent, that if I look far enough in the sequence, this has to be true because epsilon over 2 is positive. But then if I take n and m greater than or equal to that capital N, we have, now here's our application of the triangle inequality. So if I look at the difference between two elements beyond capital N, so very, very far down my sequence, well, what I can do is I can add and subtract L into this thing. So I didn't do anything, right? I added and subtracted. So if you manipulate that, you see the L completely disappears. But now we use the triangle inequality from last lecture. So this would be maybe A, this would be maybe B. And so then I can say this is xn minus L in absolute value plus xm minus L in absolute value. Now I switched the order, but because it's an absolute value, it doesn't matter what the order is here. I wrote it like this so that they look the same. And again, since I'm looking beyond capital N, I know this is smaller than epsilon over 2. And I also know that xm is within epsilon over 2 of L as well, just from the fact that I have m is greater than or equal to capital N here. And so if I add these two things together, I get that xn minus xm is less than epsilon, which tells me that xn is a Cauchy sequence. So go back if you need to and check out the definition of a Cauchy sequence to make sure that I actually did my work there and that I showed that this thing is in fact a Cauchy sequence just from the definition. Now, the really nice piece of this is sometimes it's hard to show that a sequence is not convergent just from the definition of convergence, right? So it's hard sometimes to show that everything is moving towards the same point. But one way you can rule out a convergent sequence is, by using this theorem, because if you have a convergent sequence, it also has to be Cauchy. So that tells you if your sequence is not Cauchy, then it cannot be convergent, right? You're taking the contrapositive of this thing. So let's see an example of this. Another sequence that we've seen today So let's claim, so we claim the sequence xn equal to -1 to the n is divergent. So this is the sequence that goes -1, 1, -1, 1, -1, 1, and just repeats over and over and over. Now, we can sort of intuit in our head, this thing probably isn't going to converge. It doesn't seem to be settling down anywhere. But how do we actually prove it? Well, we're going to show that it's not convergent. So proof, if xn equal to -1 to the n were convergent, then it would be Cauchy, right? We just proved that. But if you look at the difference between any two successive terms in your sequence, right? One is going to be +1 and one is going to be -1. The difference is always equal to 2 for every little n greater than or equal to 1. So taking some epsilon positive but smaller than 2, we see it is impossible to find. So it's impossible to go far enough into your sequence to find that successive terms are within epsilon of each other, because every second term is a distance of 2 apart. So such that n and m greater than or equal to n implies xn minus xm is less than epsilon. Right? So again, this is a much easier way of showing that this sequence is divergent by just showing that it's not Cauchy. And that just comes from the fact that the difference between successive terms in the sequence is always 2. So you can never look far enough in the sequence and find that everything is within epsilon of each other, because every second term is a distance of 2 away from the previous one. Okay. So we're going to continue with our exploration of sequences here. We're going to introduce another piece of nomenclature that we're going to carry with us for a long time through this lecture series. So we're going to say a sequence is called bounded. So bounded if and only if there exists a capital M in R. Sorry, that's a little bit hard to see. Let's try that again. There exists a capital M in R such that the absolute value of xn is less than or equal to m for all n greater than or equal to 1. So this means that you cannot get arbitrarily far away from 0 here, right? You can only go as far to the right on the number line as capital M and as far to the left on the number line as minus m, right? That's what it means. You're stuck in between minus m and m. That's the boundedness if you think of these as points on the real line. Now here's the nice theorem. We sort of get a chain of inequalities here, or a chain of implications. So we say if xn is Cauchy, then xn must be bounded. Okay, so we're saying this theorem here says that if you have a Cauchy sequence, then it has to be bounded. There's no way for all of your points to eventually get super close together and this thing to still be to not be bounded. Now, I want you to notice something here. We said that a convergent sequence is Cauchy, and we just said a Cauchy sequence is bounded. So we have a transitivity here. This says that if xn is convergent, then xn is Cauchy. And so from above, xn is bounded. So this tells you that convergent sequences are also bounded, right? This is the logical implication here. Convergent implies Cauchy. Cauchy implies bounded. Therefore, convergent implies bounded as well. Okay, let's come up with a proof here. Well, we're going to show that a sequence, a Cauchy sequence, is bounded. So let xn be a Cauchy sequence. So let's take, so remember with Cauchy sequences, you get to pick the value of epsilon. So I know it's Cauchy, so I choose epsilon equal to 1. Why do I choose epsilon equal to 1? Because there's only two numbers that mathematicians care about, 0 and 1, right? At least jokingly. So I can't pick 0. I'm going to choose 1 to keep things simple. We take epsilon equal to 1, and so we see that there exists a capital N such that for all n and m greater than or equal to capital N, we have that xn minus xm is less than 1. That's the definition of Cauchy. The only thing that changed here is that I picked a specific value of epsilon. So in particular, if I pick n greater than or equal to capital N, this implies, so again, if I'm going to fix the value of m to be capital N, so I get xn minus x capital N, well, this is just less than or equal to xn minus x capital N. So just under these absolute values, this is just using the definition of absolute values, which is less than or equal to xn minus x capital N, which is less than 1. This last implication here, maybe I'll put it in green, is from Cauchy. These other ones are just by understanding what the absolute value is doing. So if you need to, pause right there and try and think that out. But if I rearrange this, this gives me each xn is less than or equal to, well, it's actually just strictly less than, but it doesn't really matter, 1 plus the absolute value of x capital N for all n greater than or equal to n. So what I've done here is I've bounded infinitely many of the elements of the sequence, right? Everything beyond capital N. So if capital N is 3, every element beyond 3 is bounded by 1 plus the element at 3. If capital N is 1,000,000, then every element beyond 1,000,000 is bounded by 1 plus the millionth element of my sequence. So if we let's say m equal to the maximum of the first element in absolute value, the second element in absolute value, all the way up to the capital nth element in absolute value, and then 1 plus x capital N, we get xn is less than or equal to m for all n greater than or equal to 1. Now, why? Well, it's bigger than the first capital N elements because it's the maximum of those. And then this piece underlined in blue here is bigger than every single other element left over. And again, this is a maximum over finitely many elements. So again, you have 30 people in the room, you ask who's the oldest. Somebody has to be the oldest, right? There's finitely many people in the room. There is an oldest person there because there's only finitely many to choose from. Same thing here. There is a maximum here because there's only finitely many to choose from. And so therefore, xn is bounded. So you saw in this case, we use the Cauchy property to bound infinitely many of the terms, and you just say everything else that was left over, well, there's only finitely many to pick from, so let me pick the biggest one. Okay, now let me give you an example here, right? So I've done examples with 2 out of 3 of the sequences that we started with. We might as well round off the third one. So we say if xn is equal to n, so a sequence of just the natural numbers, then xn is not convergent. Again, fairly intuitive, right? It's just sort of going to infinity in an abstract sense. And so therefore this thing is not going to be convergent. But how do we prove this? Well, we say if xn were convergent, then it would be bounded. But for all m greater than 0, so you say, imagine there is a bound, maybe some capital M. The Archimedian property implies there exists a natural number such that n is greater than m, which implies that x sub n is greater than m. So you can always get outside of that minus m to m interval here. So xn cannot be bounded, which implies xn is not convergent. And that is sort of AKA xn is divergent here. Now, if we think about this sequence, what is happening to it? So if you took a calculus class before this, you probably have the language to describe this, but we would say that the sequence is going to infinity, right? Because we're always sort of heading right on the number line, and we are just getting bigger and bigger and bigger and bigger. So we have this abstract notion that this thing is going to infinity, but again, this is an analysis course, and therefore we have to have the precise language to say that this thing is diverging to infinity. So let's close on a definition here. So we write xn is going to infinity. So it sort of looks like it's converging, although please keep in mind, infinity is not a number. If and only if, so this is just notation, this is shorthand for saying the following. If for all m greater than 0, there exists a capital N and N such that if you look beyond that capital N, this implies xn is bigger than m. Notice there is no absolute value here, right? You have to be going rightward when you're doing this. Similarly, we write xn is approaching minus infinity if and only if for all, now not to be confusing, I'm going to use little m here. So if I choose a negative number, little m, then there exists a capital N such that for all n greater than or equal to n implies that xn is less than little m. So again, you're moving to the left on the number line and you're getting as small as possible. So I say, you know, if this thing is truly going to minus infinity, then there's got to be infinitely many elements that are beyond minus a billion, right? That's my little m term. Well, then you say, yeah, I can do that. I can find the capital N so that if you look far enough into this sequence, eventually you're going to be always smaller than minus a billion. And then always smaller than minus a billion squared, or a minus a billion to a power of a billion, right? This thing is going all the way down. Okay, so what we saw today is a basic introduction to one of the most fundamental aspects of this class, and that is sequences. We talked about what a sequence is. It's just a list of real numbers. So they are indexed by the natural numbers. You can always think of them as functions from the natural numbers to the real numbers, or you can think of them as just sort of points scattered along the real line. Once we have this notion cemented in our mind, though, we can start asking ourselves what happens as we look far into the sequence. And this led to the notion of convergence. Convergence led us to the notion of a Cauchy sequence, and Cauchy sequences led us to the notion of bounded sequences. Now, we also saw this string of logical inferences here, which said that if you are convergent, then you must be Cauchy. If you are Cauchy, you must be bounded. And therefore, if you are convergent, you are also bounded. Now, we also saw that one of the main advantages of these is for not showing convergence, but for showing divergence of a sequence. Remember, -1 to the n is not Cauchy, so therefore it can't be convergent. And just the sequence of all natural numbers is unbounded, right? It does not have, it is not a bounded sequence, and therefore it cannot be convergent.